Hello, Mr. Richens here. Welcome back to another lesson in chemistry. Today we're going to be looking again at chemical bonding in part 2. We're going to be looking at the formation of ionic bonds and covalent bonds between different types of atoms. Ionic bonding is epitomized by the reaction between sodium atoms and chlorine atoms. All right, if you go back and think about the periodic table, sodium, over here on the right side of the periodic table, and if you remember from our discussion of periodic trends, that means that sodium has a very low ionization energy. The electrons are held, that outermost electron, that s orbital electron, is held rather weakly. Whereas over here on the other side, the chlorine, it holds its electrons very tightly. With the larger nuclear charge, it's pulled the electrons in tighter. The radius of the chlorine atom is smaller than the radius of the sodium atom. And it's very difficult to remove an electron from chlorine. It takes a tremendous amount of energy. And so when we talk about ionic bonding between chlorine and sodium, what happens is that sodium loses its electron and chlorine picks it up. Or you can think of it as chlorine taking the electron away from sodium. So what does that do? Well, it produces a sodium ion and a chloride ion. And that opposite charges produce electrostatic attraction, and so the sodium ion is attracted to the chlorine ion. Now, we talked briefly about how full subshells, full energy levels, provide greater stability, lower potential energy to the ions. And so this sodium, having lost its single electron from the third energy level, is now actually slightly more stable. It has a noble gas electron configuration. It has the same electron configuration as neon. And so it's more stable having lost that electron. Chlorine, on the other hand, or the chloride ion, I should say, having gained an electron from the sodium, now has the same electron configuration as argon. And so it too has reached an noble gas configuration. This tendency to reach noble gas configurations is referred to as the octet rule. Atoms, in reacting, will attempt to achieve a complete octet, a noble gas electron configuration, full outermost S and P subshells. And in this reaction, both the sodium and the chlorine, having become chloride ion, have reached that octet. Sodium by having a full second energy level, the chloride ion now by having a full third energy level. And so if we look at this, the electron configuration, I'm going to put 2's there, for the sodium is that, and for the chloride ion, that. Okay, so, and that's going to happen with all ionic reactions. And so if we consider, let's consider calcium and chlorine. And so calcium is in the second column, so it has 2 electrons in its S subshell, plus chlorine again. But now chlorine, since it only has a vacancy, one vacancy in its outermost subshell, we're actually going to have 2 of those chlorines in order to combine with the calcium. And so when one electron from calcium will go to one chlorine atom, and the other electron will go to the other chlorine atom. And so what we end up is with calcium 2 plus 2 of the chloride ions. And of course that gives us CaCl2. And so in this case, just to go over one more time, the calcium, needing to lose 2 electrons to reach a full outermost S&P subshell, surrenders one to one chlorine atom and the other one to a second chlorine atom, resulting in the formation of 2 chloride ions and a calcium 2 plus ion. And that's how we get our calcium chloride. So, in ionic bonding, a metal generally is going to donate or transfer one or more of its electrons to a nonmetal, typically, so that both achieve full outermost S&P subshells. All right, let's next turn our attention to covalent bonding. And as a first example, let's consider diatomic fluorine. Fluorine, being a halogen, has 7 valence electrons. And if we are going to combine 2 fluorine atoms, I'm going to use a different color to represent the electrons of the other fluorine. Each of them has one unfilled orbital in the p subshell, it being occupied by only 1 electron and space for 1 more electron. In bonding, the 2 fluorine atoms are going to take advantage of that, the fact that they have an unpaired electron and they have a vacancy in their p orbital. And what's going to happen is that the 2 fluorines are going to share those 2 unpaired electrons, and this results in a shared pair. And that's the covalent bond that exists between the fluorine. Now, why is it that fluorine shares rather than just transfers one to another? It's because of a number of factors, one of which high ionization energy. It's very difficult to remove that electron from fluorine. It takes a lot of energy. Also, the decreased radius and the increased nuclear charge gives fluorine a tendency to pull electrons towards itself. Finally, removing one of those electrons would actually drive fluorine further away from an octet, actually decreasing its stability rather than increasing its stability. And so by sharing these 2 electrons, each fluorine atom achieves an octet. A shared pair counts for both of the atoms that are involved in the chemical bond. And so this fluorine has 2, 4, 6, 8, and this one has 2, 4, 6, 8. And so each is able to achieve an octet by sharing one of its electrons with another atom. Another example would be nitrogen trichloride. Nitrogen has 5 valence electrons, and chlorine, and we're going to need 3 chlorines, has 7 valence electrons. Nitrogen, since it has 3 unpaired electrons, it has a possibility of forming up to 3 covalent bonds. If another element has an unshared electron that it can use to form a shared pair, then it will. And so in the nitrogen trichloride, we end up with this arrangement. Each of the chlorine atoms shares an electron with nitrogen, and nitrogen shares one of its unpaired electrons with each of the chlorine. And so now these shared pairs, which represent or form the covalent bond between nitrogen and each of the chlorines. And so here we have one covalent bond, here we have another covalent bond, and here we have a third covalent bond. Now, in order to represent these shared pairs, chemists have adopted the convention of replacing shared pairs with a single line. And so they would represent the compound that resulted like that. And very often, the electrons on the outer atoms are not indicated. Let's consider another diatomic element. This time, let's consider O2. Oxygen has 6 valence electrons. And so it's deficient 2 electrons from achieving an octet. Once again, losing an electron would actually drive it further away from a stable situation, and so it's more likely to, with another nonmetal, share electron. And in this case, each of the unpaired electrons is going to be shared with the other oxygen to produce a situation where you have this. And now we have here in the middle 2 shared pairs. And that's referred to as a double covalent bond, and it's represented by a double line. Lastly, we have nitrogen, and as we saw before, nitrogen has 5, and so diatomic nitrogen, what do you think is going to happen? Well, if you guessed that there's actually going to be 3 shared pairs between the 2 nitrogens, you're correct. And so now we have 3 shared pairs, and this is what's known as a triple covalent bond, and it's represented by 3 lines. Now you might ask, so we have single, double, triple covalent bonds. Is it possible to form a quadruple covalent bond? It's not. This bond, the triple covalent bond, is very unstable. The fact that you've got these 3 pairs of electrons overlapping the space that they share leads to quite a bit of instability. And it takes a lot of energy to form this bond, so that when that bond is broken, a tremendous amount of energy is released, explosives and so forth. Trying to fit a 4th pair in there would just be so unstable that the atom would decompose before it even had a chance to form. Okay, to wrap up, we've talked about valence electrons being the electrons in the outermost S and P subshells and the electrons that participate in chemical bonding. We looked at Lewis structures, which is a way of representing the valence electrons, which help us in investigating how atoms might bond together and representing the types of bonds that they might form. And then finally, we looked at ionic bonding and covalent bonding, and briefly at metallic bonding. With ionic bonding, there is a transfer of electron or electrons from one atom to one or more atoms, and that resulting electrostatic attraction holds the 2 ions that result from the transfer together. In covalent bonding, you have a sharing of the 1, 2, or 3 pairs of electrons between 2 atoms to form single, double, or triple covalent bonds. That sharing holds them together.